What happens when a star collapses? The result can be a black hole, but why do some stars collapse into a black hole while others turn into neutron stars? In the next few minutes, we'll explore the incredible journey of a collapsing star and how it gives birth to one of the universe's most mysterious objects. If you're intrigued, don't forget to like, subscribe, and share. Thank you for joining us. Let's dive in. In the cold silence between stars, a faint wisp of hydrogen gas drifts, slowly gathering, nudged by gravity's quiet insistence. Over time, hundreds of thousands, even millions of years, this cloud begins to contract. The denser it becomes, the stronger its pull, drawing in more and more material from the surrounding space. As the gas compresses, friction and pressure build heat in its center. A point arrives when the temperature in the core reaches about 10 million degrees Celsius. At this threshold, something extraordinary happens. Hydrogen atoms begin to fuse. Tiny nuclei pushed together by immense pressure merge to form helium. With that fusion comes light that will shine for millions of years. A star is born. This transformation from gas cloud to star marks the beginning of a journey that will eventually lead for some stars to their collapse into black holes. A star, in simple terms, is a sphere of glowing plasma held together by gravity. Its core hosts a nuclear furnace where fusion reactions produce the energy that pushes outward against the star's own gravitational weight. This delicate balance is what allows the star to exist. On one side is the inward tug of gravity, trying to compress everything down. On the other is the outward pressure from radiation and heat, trying to expand it. The star remains stable only as long as this tug-of-war remains evenly matched. But not all stars are created equal. The fate of a star depends critically on its mass. Smaller stars like our Sun live long and gentle lives, ending as white dwarfs, small dense remnants that slowly cool over billions of years. Massive stars, however, those more than about 8 times the mass of the Sun, led more dramatic lives. Their greater mass means their cores burn hotter and faster, fusing elements up the periodic table with increasing speed. These stars may live only a few million years, brief in cosmic terms. Their destiny is shaped by the enormous forces within them, forces that will one day tear them apart. To understand why mass is so critical, imagine the difference between crushing a pillow and crushing a steel beam. The more massive a star, the more gravity it must fight to avoid collapse, and the more intense the conditions inside must be to keep fusion going. Over time, the star fuses hydrogen into helium, then helium into carbon, then carbon into oxygen, and so on. Each step requires higher temperatures and produces less energy. It is a bit like a fire that gets harder and harder to feed. The star burns through its fuel in layers, like an onion, with lighter elements fusing in the outer shells and heavier elements accumulating in the center. Eventually, the star forms a core of iron, and here lies a quiet but absolute limit in nature. Iron is the end of the road for fusion in a star. Unlike lighter elements, fusing iron does not release energy. It consumes it. And so, once a massive star accumulates too much iron in its core, fusion ceases. The outward pressure drops, and gravity, which has been waiting patiently all along, takes over. The balance that sustained the star for millions of years is suddenly gone. This moment is both swift and catastrophic. In less than a second, the core of the star begins to collapse. The iron atoms are crushed together by gravity with such intensity that electrons are forced into the nuclei, combining with protons to form neutrons. This process is called neutronization, and it begins to transform the core into a ball of neutrons. The outer layers, still falling inward, crash into this incompressible neutron-rich core. The impact rebounds, sending shockwaves outward, and the result is one of the most luminous events in the universe, a supernova. For a brief moment, the dying star can outshine its entire galaxy. Yet even in this brilliance, the core may continue to collapse. If the remaining mass is too great, above about 2 or 3 times the mass of the Sun, even neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed further, cannot hold back gravity. The collapse resumes. The core shrinks beyond any physical boundary. Space itself curves more and more sharply around it. A boundary forms, the event horizon, beyond which light cannot escape. A black hole is born. But we are still ahead of ourselves. The formation of iron, silent and invisible, deep within the star, is the quiet signal of everything that will come next. From this moment forward, the star cannot avoid its fate. It is no longer a question of if it will collapse, but how. Whether it goes out with a brilliant supernova or collapses directly into darkness depends on mass, spin, and other hidden properties. It is a moment of inevitability, a gravitational tipping point. What follows from the presence of that iron core is a cascade of physics. Pressure plummeting, gravity accelerating, particles crushed into more fundamental forms. In a laboratory, we cannot recreate these conditions. The star becomes a machine of extremes, heat, density, and curvature of space. We can only model it in equations and look to the sky for evidence. And yet, despite the vastness of these energies and scales, the process begins with something so unassuming, the quiet formation of iron at the core of a dying star. A question lingers, soft and unsolved. Why does nature choose this boundary? Why iron? Why not a universe where heavier elements still yield energy through fusion? In this, there is a kind of cosmic ceiling written into the physics of atomic nuclei, a boundary that forces collapse, that shapes the existence of neutron stars and black holes. Stars live and die by these limits, written into the fabric of the strong nuclear force and the nature of quantum interactions. Somewhere, in a galaxy far from our own, a massive star burns near the end of its life. Its core is heavy with iron. Its light, still steady, masks the drama within. No one can see the moment balance is lost, but when it comes, it will come quickly. The silence in the core will break. Gravity will win. The quiet inevitability of collapse begins with iron, but the descent into destruction is anything but simple. As the core of a massive star becomes dominated by iron, the physical balance that once defined its life starts to unravel. The fusion reactions that once released energy to counter gravity now cease. With no energy to push outward, gravity takes the lead, dragging the core inward. What follows is a chain reaction of physics operating at the most extreme densities and temperatures known in the universe. In just a fraction of a second, the entire core begins to collapse under its own weight, accelerating towards something more compact and more mysterious than anything the star has ever known. The first stages of collapse happen on a microscopic level. As gravity crushes the iron core, the density rises to such an extent that electrons are forced into atomic nuclei. There they combine with protons to form neutrons in a process called electron capture. This transformation releases a burst of neutrinos, nearly massless particles that barely interact with matter and escape the star at nearly the speed of light. Electron capture is one of the earliest and fastest processes during collapse, and it contributes to the increasing density of the core. At the same time, another dramatic process begins: photodisintegration. The core is now so hot, exceeding billions of degrees, that high-energy photons or particles of light start breaking apart atomic nuclei. Iron atoms are smashed into helium nuclei, and those in turn are torn into protons and neutrons. This disassembly of matter consumes energy, making the core collapse even faster. Photodisintegration can be thought of as a reversal of the fusion process that built the star's structure in the first place. Instead of combining smaller atoms into heavier ones, the collapse is now stripping atoms apart, converting structured matter into its raw components. This process is catastrophic for the star's stability. It robs the core of energy and accelerates the implosion. With every passing microsecond, the core grows denser. When the density surpasses about 400 million tons per cubic centimetre, comparable to compressing Mount Everest into the volume of a sugar cube, the core becomes so tightly packed that further collapse is resisted, not by heat or pressure, but by the degeneracy pressure of neutrons. Degeneracy pressure is a quantum mechanical effect. It arises because neutrons, like electrons, are fermions, particles that cannot occupy the same quantum state in the same place. When the neutrons are compressed closely enough, this rule resists further compression, acting like an invisible spring pushing outward against gravity. If the core's mass is below a certain threshold, approximately 2 to 3 times the mass of the Sun, this degeneracy pressure halts the collapse. The infalling material rebounds off the incompressible core, creating a shock wave that travels outward. But the shock wave faces resistance from the outer layers and from the energy loss caused by the earlier emission of neutrinos. In some cases, this shock wave stalls. But if enough energy is deposited by the outgoing neutrinos, an idea still under active investigation in astrophysics, the shock wave can be revived, tearing through the star's outer layers and blasting them into space. This is a core collapse supernova. It is among the brightest events in the cosmos, briefly radiating more energy than the star did over its entire life. This outward blast leaves behind a compact remnant at the center, the neutron star. A neutron star is a city-sized object with a mass greater than the Sun. It is so dense that a teaspoon of its material would weigh about 1 billion tons. Its gravity is immense, its surface smooth and hard. It spins rapidly, sometimes hundreds of times per second, and emits beams of radiation from its magnetic poles. When these beams sweep past Earth, we detect them as pulses, leading to the name pulsar. Despite its violence, the birth of a neutron star is, in a strange way, a survival story. The collapse is stopped. Matter is preserved in a new form. But not every collapse ends here. If the core is too massive, neutron degeneracy pressure is not enough. The core continues to collapse. No known force can resist gravity at this scale. The neutrons themselves are crushed. The density becomes so great and the curvature of space so intense that a boundary forms around the collapsing region. This is the event horizon, the invisible surface beyond which nothing, not even light, can return. To an outside observer, this marks the point of no return. The collapse continues inside, but its details are hidden from view. Time, from an outside perspective, appears to slow near the event horizon, and the final stage of collapse seems to freeze. But in the star's own frame, the process proceeds quickly and unstoppably. The core vanishes into a region where gravity dominates all else. A black hole is not a physical object in the traditional sense. It is a region of space where matter has collapsed to a point known as a singularity. This point is where our known laws of physics break down. Density becomes infinite, and space-time is so warped that the equations of general relativity cannot describe it fully. We know the black hole by its effects, by the way it warps the paths of nearby stars, or by the X-rays emitted by matter spiraling into it. but the singularity itself remains hidden. The very concept of location becomes meaningless inside a singularity. Matter, time, and direction all lose their familiar roles. There is a sobering beauty in this outcome. A star that once lit its surroundings, that formed in the gentle swirl of hydrogen and helium, now vanishes into the geometry of space-time. It leaves behind no surface, no shell, no mark but gravity. And yet, it is not lost. The mass and momentum remain. The gravitational field continues to shape its surroundings. The black hole becomes a dark architect, unseen but present, curving the universe in its vicinity. Even now, scientists debate the exact mechanics of this transformation. What happens in the final milliseconds before the event horizon forms? Do quantum effects soften the singularity? Could new states of matter emerge? These are not questions of idle speculation. They are at the forefront of modern astrophysics. They point to a junction between Einstein's theory of general relativity and the rules of quantum mechanics, a junction we do not yet fully understand. In the sky, a supernova flares and then fades. What remains may be a neutron star spinning and flashing like a cosmic lighthouse, or it may be a black hole, utterly silent. And though we cannot see the collapse directly, we trace its consequences. In this way, the star's final act, shaped by the physics of collapse, continues to ripple through space, echoing long after the light has vanished. Even in the quiet aftermath of collapse, gravity continues its work. A black hole, once formed, does not simply sit in space. It influences its environment with intense focused gravity, bending the paths of nearby stars and distorting the fabric of space around it. But before this gravitational well settles into its invisible state, the exact way it forms depends not only on mass but on more subtle conditions inside the star. One of the most important of these is rotation. Like a figure skater pulling in their arms to spin faster, a collapsing star rotates more rapidly as its size shrinks. This conservation of angular momentum can have profound effects. Rotation can flatten the collapsing material into a disc-like structure around the core and delay the collapse itself in some cases. It also plays a critical role in how matter and energy are distributed during the explosion, or whether an explosion occurs at all. A fast-spinning star may eject more material outward or funnel energy into narrow beams, shaping the supernova or leading to the formation of relativistic jets. These jets, high-speed outflows of matter, are often seen in gamma-ray bursts, some of the most energetic explosions in the cosmos. The connection between rotation and the kind of black hole that forms is an active area of research. A spinning black hole is different from a non-spinning one. The equations of general relativity allow for both, but a rotating black hole, described by the Kerr solution, drags the very fabric of space around it, creating what is known as frame dragging. Objects near the black hole do not just fall inward, they are also twisted around its axis. Caught in a swirl of space-time itself, this rotational property could influence the black hole's ability to accrete matter and to power jets, making it not just a passive object but an active engine of cosmic structure. Another factor shaping the collapse is metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium in a star. Stars with higher metallicity tend to lose more mass over time through strong stellar winds. This mass loss can alter the star's ultimate fate. A star that begins its life with, say, 30 solar masses but loses half of that mass before collapsing may avoid becoming a black hole entirely, ending instead as a neutron star. In contrast, low metallicity stars, common in the early universe, retain more of their mass and are more likely to collapse directly into black holes. The role of metallicity ties the physics of collapse to the chemical history of the cosmos. It links black hole formation not just to mass and gravity, but to the legacy of earlier generations of stars which seeded the universe with heavier elements. In this way, black hole formation is not a standalone event. It is the outcome of a history written in starlight and stellar ashes. Magnetic fields, too, may shape collapse outcomes. Though often neglected in early models, strong magnetic fields can affect the behavior of charged particles in the collapsing core. They may channel energy along field lines, influence the structure of accretion disks, and even help launch jets. In rapidly rotating, magnetized stars, these fields may be twisted and amplified during collapse, producing complex dynamics. In extreme cases, they might halt collapse temporarily, leading to delayed black hole formation or exotic transient events. The interplay of rotation, magnetic fields, and collapse is still not fully understood, but it suggests that black holes are not always formed in the same way. They are shaped by initial conditions and fine details, tiny asymmetries and hidden forces written into the life history of the star. In some stars, these additional forces may not lead to a supernova at all. Instead, the star might undergo what astronomers call a failed supernova. In this scenario, the core collapses into a black hole, but the shockwave needed to blow off the outer layers never materializes, or it quickly stalls. With nothing to halt the infall, the outer material collapses as well, disappearing silently into the newly formed black hole. From the outside, the star simply vanishes. Its light dims, and no dramatic explosion marks its end. This idea is supported by observations of massive stars, red supergiants for example, that seem to disappear from the sky without an accompanying supernova. These silent deaths are difficult to confirm, but they may represent an important population of black hole births, especially among the most massive stars. The idea of direct collapse challenges earlier assumptions that all black holes are born in a blaze of supernova light. It suggests that nature may offer a quieter route to black hole formation, one without violent ejection, without the seeding of heavy elements into the surrounding space. These silent collapses may help explain the existence of very massive black holes in the early universe, objects that seem too large to have grown so quickly through gradual mergers and accretion alone. If massive stars can collapse directly into massive black holes, the timeline becomes more plausible. In this sense, the pathways of collapse also shape our understanding of galaxy formation and cosmic evolution. Yet even when explosions do occur, the resulting dynamics are anything but simple. The expelled outer layers of the star enrich the surrounding interstellar medium with heavy elements, carbon, oxygen, silicon, and more. These elements will be incorporated into future stars, planets, and eventually the chemistry of life. Meanwhile, the compact core is left behind, now either a neutron star or a black hole. If it is a black hole, it begins its invisible life. Its gravity may draw in nearby material, forming a glowing accretion disk. The friction in this disk heats matter to millions of degrees, emitting X-rays and gamma rays that can be observed with space telescopes. In some systems, especially where the black hole orbits a companion star, matter from the companion can be pulled in, creating a persistent high-energy signal that reveals the black hole's presence. Even without a visible surface, even without light of its own, the black hole makes itself known by the way it affects its surroundings. In recent years, new tools have begun to open the curtain further. The detection of gravitational waves, ripples in the fabric of space-time, has allowed astronomers to observe black holes merging, events so distant and quiet that no light accompanies them, only a brief shiver in the geometry of the cosmos. These waves offer a new way to study black holes, not through the matter they influence, but through the space-time they disturb. In this way, our understanding of black holes grows not only through explosions and light, but through silence and distortion. Still, the process that leads from a massive star to a black hole is shaped by variables we do not yet fully understand. Why do some cores explode while others fail? What is the exact role of magnetic fields in launching relativistic jets? How does rotation determine the final spin of a black hole? These questions continue to guide research, each answer leading deeper into the physics of collapse. In the end, the formation of a black hole is not one process but many, intertwined in a web of forces and conditions. From the quiet fusion of iron to the twisting of space-time, from the silence of failed supernovae to the tremor of gravitational waves, each black hole tells a story written in gravity, in collapse, and in the deep rhythms of the cosmos. As astronomers peer deeper into the cosmos, they begin to stitch together evidence that supports these diverse pathways to black hole formation. Yet much of what we know about black holes does not come from observing the collapse itself. It comes from studying what is left behind. A black hole, by definition, emits no light. It is the absence of light, the removal of signal, that tells us something is there, and so we infer their presence through the behavior of nearby stars, the glow of hot gas spiraling inward, or the ripple of gravitational waves traveling across the universe. One of the most direct ways to detect a stellar mass black hole is by observing a binary system, where two stars orbit each other. If one star in such a system collapses into a black hole, its gravitational influence remains. The visible star continues to orbit the dark companion, and that motion can be tracked. If the visible star moves as if pulled by an unseen mass, and if that mass exceeds the known limits of neutron stars, roughly 2 to 3 solar masses, then the object is almost certainly a black hole. This method, called dynamical detection, has revealed several black holes in our own galaxy. These stellar mass black holes typically have masses between 5 and 20 solar masses, though some are larger. They are relics of once bright stars, long extinguished, now dark and dense beyond imagination. Another avenue of discovery lies in the radiation emitted by material as it falls toward a black hole. This material, often gas stripped from a companion star, forms an accretion disk as it spirals inward. The friction in this disk heats it to millions of degrees, causing it to emit high-energy X-rays. X-ray binaries, systems where a visible star orbits a source of X-rays, are among the most reliable indicators of stellar mass black holes. Their flickering emissions and periodic variations give clues about the nature and size of the invisible partner. In some cases, the X-ray emission is modulated by strong magnetic fields or altered by the warping of space-time near the event horizon. These distortions offer indirect glimpses into the behavior of matter under conditions that cannot be reproduced in any laboratory on Earth. The geometry of the disk, the spin of the black hole, and the rate of infall all shape the light that we eventually observe. Even though the black hole itself remains hidden, the environment around it speaks loudly. Then there are the mergers, cosmic collisions between black holes that send out tremors in space-time. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of such waves. Two black holes, each around 30 solar masses, spiraled into one another and coalesced into a single, more massive black hole. The energy released in that collision, converted briefly into gravitational waves, was greater than the combined luminosity of all the stars in the observable universe. Yet the event was completely dark. No flash, no explosion, just a ripple in the geometry of space, travelling for over 1 billion years before reaching Earth. Since that first detection, dozens more have followed, revealing a surprising diversity in the masses and frequencies of black hole mergers. These observations have transformed our understanding of how black holes form and interact, confirming that they are not rare anomalies but common byproducts of stellar evolution. Still, questions remain. Some of the detected black holes are more massive than models of stellar collapse had predicted. How do such large black holes form? Could some result from the merger of smaller black holes over time, building up mass through repeated collisions? Or are there pathways, perhaps involving low metallicity stars or unusual binary interactions, that allow stars to collapse directly into very massive black holes? These possibilities challenge our assumptions and expand the range of stellar fates. In particular, the discovery of black holes in the so-called mass gap, a range between roughly 50 and 100 solar masses, where traditional stellar evolution models predict no black holes should exist, has forced theorists to reconsider what is physically possible during collapse. Some suggest that under specific conditions, stars could avoid shedding mass and collapse directly into black holes within this gap. Others explore more exotic physics, such as pair instability supernovae, where the production of electron-positron pairs in the core alters the collapse behavior. Each observation leads to new questions, and each question drives deeper inquiry into the forces shaping stellar death. Beyond detection, scientists also study the statistical patterns in black hole populations. How many stellar mass black holes exist in the Milky Way? Estimates suggest there may be hundreds of millions, most of them silent and undetected, drifting through the galaxy without companion stars or accretion disks. They are dark islands in space, moving invisibly, their only clue to existence being their gravitational effect on nearby stars or gas clouds. Efforts to detect these hidden black holes include monitoring the light of distant stars for microlensing events, brief, subtle brightening caused by a compact object passing in front of the star and magnifying its light. While such events are rare and difficult to confirm, they offer a tantalizing method for uncovering otherwise invisible black holes scattered across the galaxy. There is also a growing effort to simulate the entire life cycle of massive stars in high-resolution computer models, tracing their evolution from initial formation to final collapse. These models must account for nuclear reactions, convection, rotation, magnetic fields, and fluid instabilities, all while solving the equations of general relativity. They are computationally demanding and complex, but they provide insights into which conditions lead to supernova explosions, which lead to black holes, and which walk the delicate line between. The models are compared with observed supernova light curves, neutrino emissions, and gravitational wave signals to test their accuracy. As observations improve, so do the models, refining our understanding of the processes that lead from brilliant starlight to eternal darkness. Amid all this complexity, one truth remains clear. The birth of a black hole is a story of limits. The limit of fusion to support a star, the limit of pressure to resist collapse, the limit of light to escape gravity. Each of these thresholds is crossed during the final stages of stellar evolution, marking points where the familiar laws of physics strain and bend. It is at these limits that black holes are born, not as mythical anomalies, but as the natural result of well-understood forces taken to their extremes. Yet despite our knowledge, the formation of a black hole remains an awe-inspiring process. From the slow fusion of hydrogen in a young star's heart to the unstoppable collapse into an event horizon, the path is long, intricate, and still not fully charted. Somewhere in a quiet corner of a distant galaxy, another massive star nears its end. Its iron core is growing. Neutrinos are beginning to whisper their way outward. The collapse has not yet begun, but the stage is set. In time, perhaps soon, it too will cross a threshold beyond return, and gravity will write another black hole into the darkness. Even after the black hole has formed, its influence continues to shape the surrounding universe. The most dramatic consequence of a black hole's existence is its ability to curve space-time itself, bending light, warping trajectories, and distorting the very fabric of space. This curvature grows more intense as one approaches the event horizon, the point beyond which escape becomes impossible. The event horizon represents the threshold between the observable universe and the hidden interior of the black hole. Once something crosses it, whether it is light, gas, or even entire stars, it is lost to view, swallowed by the singularity at the core of the black hole. The singularity itself, the heart of the black hole, is where gravitational forces become infinite, and the laws of physics as we know them break down. In the neighbourhood of a black hole, gravity is so strong that it significantly alters the passage of time. This phenomenon, known as time dilation, means that time, as experienced by an object near the event horizon, slows down relative to the time experienced by an observer far away. If one were to observe an object falling into a black hole, it would appear to move slower and slower as it neared the event horizon, its image becoming increasingly redshifted until it fades completely. From the object's perspective, however, time continues normally, and it crosses the event horizon in an instant, experiencing no such slowing of time. The bending of light and time around a black hole, while bizarre and unsettling, is not merely theoretical. It has been observed and measured. One of the most iconic images in modern astrophysics is that of the shadow of a black hole, captured by the Event Horizon Telescope in 2019. This image, the first ever photograph of a black hole, revealed the presence of an enormous black hole in the centre of the galaxy M87. It provided direct visual evidence of the event horizon's influence on light, showing a dark region surrounded by a glowing ring of superheated gas. The shadow's size and shape were consistent with predictions made by general relativity, confirming that black holes behave as expected according to Einstein's theory. Yet, despite this success, the black hole's singularity remains elusive. We know it is there, and we know it marks a region where the fabric of space-time is torn, but we cannot directly observe what happens inside it. The singularity's nature is one of the greatest mysteries in physics. Current theories suggest that quantum mechanics, which governs the smallest scales of reality, and general relativity, which governs the largest scales, are incompatible within the singularity. At the singularity, the two sets of laws break down, and new physics may be required to fully explain the behaviour of matter and energy at this point. One of the leading ideas in theoretical physics is that quantum gravity, an as yet unproven theory that seeks to reconcile general relativity with quantum mechanics, may hold the key to understanding the singularity. In quantum gravity, space-time itself is thought to be quantized, made up of discrete units, much like how matter is made up of atoms. If this theory holds true, it might explain the infinitely dense nature of the singularity. Some scientists speculate that at the singularity, the density of matter might not be infinite after all, but rather extremely high and confined to a minuscule region, where the very concept of location no longer applies. This is known as the quantum foam of space-time, a hypothesis that remains speculative, but offers a glimpse into the potential behaviour of matter and space at the smallest scales. Until a theory of quantum gravity is developed, we are left to study the outer limits of black holes, observing their effects on their surroundings and using these observations to infer their properties. This indirect approach to studying black holes has led to some remarkable discoveries. For instance, black holes are not static objects. They can grow and evolve over time, As they accumulate mass from their environment, they can become even more massive, sometimes reaching millions or even billions of times the mass of the Sun. These supermassive black holes are thought to reside at the centers of most galaxies, including our own Milky Way. The growth of these supermassive black holes is a key aspect of galaxy formation and evolution. It is believed that they grow by accreting gas from their surroundings, or by merging with other black holes. The immense gravitational pull of supermassive black holes can influence the motion of stars and gas in the galaxy, shaping the overall structure of the galaxy itself. Furthermore, black holes are believed to play a role in regulating the growth of galaxies. The energy released by the accretion of matter into a black hole, in the form of radiation and powerful jets, can heat up the surrounding gas and prevent it from collapsing into new stars. This process, known as feedback, is thought to be a critical factor in the evolution of galaxies, influencing their size, shape, and star formation rates. Even as they remain invisible in the traditional sense, black holes leave their mark on the universe, shaping the structures around them in profound ways. Their presence is felt in the motion of stars, the dynamics of galaxies, and the very fabric of space-time itself. Yet black holes remain mysterious in another way. They've been proposed as potential portals to other regions of space-time, and some theories suggest that they might be connected to other universes in what is known as the multiverse hypothesis. While this idea remains speculative and unproven, it has captured the imagination of many physicists and cosmologists. In the context of black holes, the multiverse hypothesis posits that the singularity could be a gateway to another universe, where the laws of physics might be different. This idea raises profound questions about the nature of reality, the structure of the cosmos, and the limits of human understanding. It also suggests that black holes may not be the ultimate boundary of space-time, but rather a bridge to other realms of existence. Despite these fascinating ideas, it's important to recognize that we're still in the early stages of understanding black holes. There is much more to learn about these enigmatic objects, from the details of their formation to the full implications of their existence. New observational techniques, such as gravitational wave astronomy, are providing fresh insights into the behavior of black holes, and new theories of quantum gravity may one day reveal the true nature of the singularity. For now, however, we can only continue to study the effects of black holes on the universe, piecing together the clues they leave behind. In the end, black holes remind us of the vastness and complexity of the cosmos, and of how much there is still to discover. Their formation, their influence on the surrounding universe, and their ultimate mysteries all point to the limits of human knowledge, and the continuing search for understanding in a universe that remains, in many ways, profoundly unknowable. The study of black holes may be one of the greatest scientific endeavors of our time, but it is also a humbling reminder of the infinite mysteries that still await us. As we move outward from the singularity's unknowable depths and the warped space-time near the event horizon, we begin to understand how black holes continue to interact with the universe long after their birth. Despite their name, black holes are not simply voids or emptiness. They are, in every sense, objects, with mass, spin, and a gravitational presence that continues to shape their surroundings. In fact, black holes can act as engines of galactic evolution. Their gravitational pull can trap enormous quantities of matter, and as this matter spirals inward, it releases tremendous amounts of energy in the form of light and radiation. This process of accretion is not a quiet one. Matter falling into a black hole is heated by friction and compression as it forms an accretion disk. The temperatures in this disk can rise into the millions of degrees, producing X-rays and gamma rays that illuminate the region just outside the event horizon. In some systems, this radiation can be so powerful that it outshines the combined light of all the stars in the host galaxy. The resulting object is called a quasar, short for quasi-stellar radio source, though the term does not capture the scale of its output. A single quasar can emit more energy than an entire galaxy for millions of years, powered by a supermassive black hole consuming matter at its core. These supermassive black holes, often containing millions or even billions of solar masses, are now believed to reside at the center of nearly every large galaxy, including our own Milky Way. The evidence is strongest at the galactic center, where stars orbit around an invisible mass with speeds so high that only a compact object with millions of times the Sun's mass could explain it. In the Milky Way, this central object is known as Sagittarius A, a radio source located about 26,000 light-years from Earth. Its gravitational influence governs the motion of stars within a few light-years of its position. Though quiet now, it likely had periods of intense activity in the past, when it accreted large amounts of gas and emitted powerful radiation. These periods of activity are thought to regulate star formation across the galaxy. When a black hole feeds on its environment, it can generate jets, narrow streams of high-energy particles launch from the regions around the event horizon. These jets can extend for thousands of light-years and can heat or sweep away the gas needed to form new stars. This feedback mechanism helps explain why galaxies appear to stop growing beyond a certain size, and why the largest galaxies tend to have the most massive black holes at their centers. The black hole, though tiny in size compared to its host galaxy, acts as a kind of cosmic thermostat. The role of black holes in galaxy formation reveals the connection between stellar collapse and large-scale cosmic structure. What begins as a dying star can, through accumulation and growth, become the gravitational core of an entire galaxy. Over billions of years, mergers between galaxies bring together their central black holes, and the black holes themselves merge, growing larger in the process. Each merger sends out a final wave of gravitational radiation, a signal of mass and motion that echoes across the universe. The recent detections of these waves by observatories like LIGO and Virgo have opened a new way of observing black holes, independent of light. These observations not only confirm the predictions of general relativity, but also give us clues about the populations of black holes in the universe, their masses, spins, and frequencies of merger. Each signal is a brief, low, murmuring tone in the fabric of space-time, and together they form a quiet symphony of collapse. Even isolated black holes, those not in binary systems or feeding on nearby matter, can leave detectable traces. As they pass through clouds of interstellar gas, their gravity can create wakes, disturbances in the gas flow that may someday be visible with sensitive telescopes, or they might reveal themselves through microlensing when their gravity magnifies the light of a background star. These events are rare and subtle, but they offer one of the only means of detecting so-called dark black holes, those with no luminous companions or accretion disks. As instruments improve, and as sky surveys become more detailed and comprehensive, the census of black holes will grow. We're only beginning to glimpse the full population of these objects. But black holes also challenge our assumptions in more philosophical ways. They raise questions about the nature of information and whether it can ever truly be lost. When matter falls into a black hole, what happens to the information it contains? This is the heart of what physicists call the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Yet, once something passes the event horizon, it seems to disappear, leaving only mass, charge, and spin behind. Stephen Hawking famously proposed that black holes could emit radiation, a process now called Hawking radiation, through quantum effects near the event horizon. This radiation would slowly cause the black hole to lose mass and eventually evaporate over enormous timescales. But if the black hole evaporates, what happens to the information it once contained? Does it re-emerge in the radiation? Is it encoded in some subtle structure on the event horizon? Or is it lost forever, violating the principles of quantum mechanics? No one knows for certain. This paradox has prompted intense debate and inspired many proposed solutions, ranging from holographic principles to exotic space-time geometries. Whatever the answer, it will almost certainly require a new synthesis of quantum theory and general relativity, a unified theory of quantum gravity. While this search for unification continues, black holes remain among the best natural laboratories for testing the limits of our physical theories. They are the most extreme environments in the known universe, where gravity reaches its strongest and time becomes deeply entangled with space. They allow us to study matter at high energy densities, to probe the behavior of light in curved space, and to observe phenomena that stretch our conceptual boundaries. And yet, for all their extremity, they are also surprisingly simple. According to the no-hair theorem, a black hole can be fully described by just three properties: its mass, its spin, and its electric charge. All other details, the structure of the original star, the complexity of its collapse, are lost. In this way, black holes erase the history of their formation, reducing it to a minimal set of parameters. This simplicity is both elegant and unsettling. It strips away complexity, leaving behind a pure expression of gravitational collapse. Still, the simplicity is only skin deep. The environments around black holes, shaped by magnetic fields, accretion flows, and radiation, are anything but simple. These chaotic surroundings offer rich observational opportunities. Telescopes continue to scan the skies, looking for flares of X-rays, the rhythmic flicker of accreting material, and the quiet swell of gravitational waves. Each new signal helps refine our understanding, not just of black holes themselves, but of the stars and galaxies from which they form. The black hole is the endpoint of stellar collapse, but it is also the beginning of new questions. Its horizon marks not just a boundary in space, but a frontier in knowledge. Somewhere a star has already passed that threshold. Its light is gone, its mass transformed. The story it once told through its radiation has ended, but its influence continues, shaping orbits, stirring gas, distorting light, and whispering through space-time. It has joined the silent population of collapsed stars that now guide the structure of galaxies and the direction of scientific curiosity. In this darkness there is not absence, but deep presence. A black hole is not the end of a star's life. It is the continuation of its gravity. While the core structure of a black hole may be mathematically simple, the path to its formation is anything but. To trace that journey back through time is to follow a sequence of precise physical steps shaped by mass, composition, temperature, and motion. At the center of this process lies the massive progenitor star, an object whose fusion reactions build heavier and heavier elements, until, ultimately, an iron core forms and tips the balance toward gravitational collapse. But even at this pivotal stage, the final outcome is not fixed. Whether the collapse ends in a neutron star, a black hole, or even fails to produce an observable supernova depends on the intricate physics unfolding in fractions of a second. As the core compresses, its pressure rises, its density climbs, and its particles undergo transformations. Electrons are captured by protons to form neutrons, and the remaining matter experiences photodisintegration, where nuclei are torn apart by high-energy radiation. These processes remove the last sources of pressure support and hasten the collapse. In this dense interior, neutrinos, particles with barely any mass and almost no interaction with matter carry away enormous amounts of energy. They are born in vast quantities during collapse, and although most escape, a small fraction interact with surrounding material, depositing energy that may revive the shockwave initiated by the rebounding core. Whether this shockwave succeeds in blowing off the outer layers of the star determines whether we observe a supernova, or whether the collapse continues unimpeded into the birth of a black hole. In failed supernova, the shockwave stalls before it can eject the envelope. The star fades without a final blaze, its core falling into itself, its mass disappearing into the growing gravitational well. From the outside, the event appears as a vanishing act. A luminous supergiant simply dims and does not reappear. Such disappearances are rare but have been tentatively identified in observational surveys. These silent endings are particularly important because they may explain how the most massive black holes in the universe formed so early in cosmic history. If very massive stars in the early universe could collapse directly into black holes without losing much mass to explosion, they could provide the seeds for the growth of supermassive black holes within just a few 100 million years of the Big Bang. Observations of bright quasars in the young universe strongly suggest that such rapid formation must have occurred. The mechanism of direct collapse, bypassing a luminous supernova, offers a plausible route. The metallicity of the progenitor star plays a major role here. Stars with low metallicity lose less mass through stellar winds, allowing them to retain more of their initial mass throughout their lives. This is especially relevant for stars in the early universe, which formed from primordial hydrogen and helium with only trace amounts of heavier elements. These metal-poor stars, sometimes referred to as population 3 stars, are thought to have been extremely massive, perhaps several hundred times the mass of the Sun. Their collapse may have produced the first generation of black holes, which then grew through accretion and mergers to become the supermassive black holes we see today at galactic centers. Although no population 3 star has yet been observed directly, their existence is strongly supported by models of chemical evolution and by the absence of certain elements in the oldest known stars. Rotation, too, adds complexity. A rapidly spinning core can flatten the collapsing material into a disk, leading to asymmetric explosions, high-energy jets, and in some cases, gamma-ray bursts. Brief but intense emissions of gamma rays that are among the most luminous events in the universe. These bursts are thought to occur when a massive, rapidly rotating star collapses into a black hole, and a jet of particles is launched along its rotational axis. If Earth lies along the path of that jet, we observe a powerful flash of gamma rays lasting a few seconds. These events, while rare, provide crucial evidence for black hole formation in the moments of collapse. They also show how the internal dynamics of the progenitor star, its spin rate, magnetic field, and internal mixing, can affect the observable outcome. Magnetic fields, though difficult to model, are thought to play an important role in channeling energy during collapse. In magnetorotational models, strong fields can extract angular momentum from the inner core and help power jets or influence the geometry of the explosion. These fields may arise from dynamo processes inside the star or may be amplified during collapse. In certain models, extremely strong magnetic fields and rapid rotation combine to form a magnetar, a highly magnetized neutron star, but in more massive progenitors, this combination may instead lead directly to a black hole. The distinctions are subtle, shaped by small differences in mass, field strength, and angular momentum. From a theoretical perspective, modeling core collapse is among the most challenging problems in astrophysics. Simulations must track fluid motion, radiation, magnetic fields, nuclear reactions, and gravitational effects in 3 dimensions, often with microsecond precision. Different models predict different outcomes for the same initial conditions, depending on how various processes are treated. One key uncertainty is the equation of state, the relationship between pressure, density, and temperature for matter at nuclear densities. This equation governs whether the collapsing core stabilizes as a neutron star or continues inward to form a black hole. Small differences in this equation can change the threshold between stability and collapse. Despite these uncertainties, certain patterns emerge. Progenitors below roughly 8 solar masses produce white dwarfs. Those between about 8 and 25 solar masses tend to form neutron stars. Above this, the probability of black hole formation increases, especially if rotation and metallicity favor mass retention. The most massive stars, above perhaps 40 solar masses, are the most likely to undergo direct collapse. These boundaries are not sharp. Rather, they are regions in a multidimensional parameter space shaped by mass, rotation, chemical composition, binarity, and age. Binaries complicate the picture further. In systems where two massive stars orbit each other, mass transfer can strip one star of its envelope, altering its evolution. The surviving core may be more compact and more likely to collapse directly. Alternatively, the interaction may cause the stars to merge, forming a single, more massive object prone to black hole formation. In extreme cases, both stars may collapse into black holes and later merge, producing a gravitational wave signal detectable on Earth. These scenarios are not just theoretical. They have been observed through gravitational wave detections, each carrying a story of intertwined stellar lives ending in collision. So, while the basic framework of black hole formation is rooted in mass and gravity, the full story is one of complexity, diversity, and chance. Stars do not die in identical ways. Their fates are shaped by how they spin, what they're made of, how they interact with companions, and how the physics of their cores unfolds in the final seconds. Every black hole that forms is a summary of a life lived in nuclear fire and gravitational balance, ended by collapse and sealed by light's departure. Each one carries a memory of the star it once was, though the details are hidden behind the veil of the event horizon. The formation of a black hole is the final irreversible stage of a massive star's life, but it also marks the beginning of a new set of cosmic questions. As we observe the consequences of black hole formation, we must confront the fact that these objects, despite being some of the most studied phenomena in astrophysics, are still not fully understood. Their central feature, the singularity, remains an enigma. The singularity is a point in space-time where density becomes infinite, and the curvature of space-time becomes infinite as well. It is a region where our understanding of physics breaks down completely. The laws of general relativity, which describe the behavior of gravity on large scales, no longer apply. Similarly, quantum mechanics, which governs the behavior of the smallest particles, also fails to give us an accurate description of what occurs within this region. The singularity itself is hidden from view by the event horizon, the boundary around a black hole beyond which no information can escape. But this boundary itself is not a hard edge, as one might imagine. It is a shifting dynamic surface defined by the black hole's mass and spin. While we cannot see inside a black hole directly, we can infer much about their properties by studying the way they interact with their environment. The behavior of matter in the accretion disk, the structure of the jets, and the distortions in light and time as they near the event horizon all provide clues. Yet despite these clues, the singularity remains a place where our understanding falters and our most fundamental theories of physics cease to work. To some, this is the most profound mystery that black holes present. How does matter behave at such extreme conditions? How do quantum mechanics and general relativity, two pillars of modern physics, reconcile in the environment of a black hole? The answer to these questions lies in the quest for a theory of quantum gravity, an elusive framework that could bring together the gravitational forces that govern black holes with the quantum forces that govern elementary particles. Theoretical physicists continue to explore various models such as string theory and loop quantum gravity, but these ideas have yet to provide a definitive answer. It is clear that black holes are not merely laboratories for testing our theories, they are also objects that challenge the very foundations of our understanding of space, time, and matter. For now, the singularity stands as a stark reminder of the limits of knowledge. However, there is another aspect of black holes that has fascinated physicists and astronomers alike: their apparent simplicity. Once a black hole forms, it can be described by just three properties: mass, spin, and charge. This remarkable property is known as the no-hair theorem, which asserts that a black hole's external features can be determined entirely by these three parameters. All other information about the star from which it formed, about the specific processes that led to its collapse, disappears behind the event horizon. This simplicity may seem paradoxical, given the chaotic and complex processes that precede black hole formation. The fact that a black hole is ultimately described by such a small number of parameters raises profound questions about the nature of information and the structure of the universe. Some physicists speculate that this simplicity is not a coincidence, but a clue to deeper principles of nature. Perhaps they suggest the universe operates according to some hidden order, and black holes are just one manifestation of this underlying simplicity. The relationship between black holes and information has also led to the black hole information paradox. This paradox arises because, according to the laws of quantum mechanics, information cannot be lost. However, once matter falls into a black hole, it appears to be permanently lost to the universe, its information irretrievably trapped behind the event horizon. The implications of this paradox are profound, as it challenges one of the most fundamental principles of quantum theory. Several theories have been proposed to resolve this paradox. One possibility is that information is not lost, but is instead encoded in the radiation emitted by the black hole, a process known as Hawking radiation. According to Stephen Hawking's famous theory, black holes slowly evaporate over time, emitting radiation due to quantum effects near the event horizon. This radiation carries away information, potentially allowing the information that falls into a black hole to be recovered, albeit in a highly scrambled form. However, the precise nature of this process remains unclear, and the debate over whether or not information can truly escape from a black hole continues to be one of the most active areas of research in theoretical physics. Regardless of the ultimate resolution of the information paradox, the quest to understand black holes is also a quest to understand the fundamental nature of reality. It is a search for the deepest truths about the fabric of the universe, about how space and time are woven together, and about how the forces of gravity, quantum mechanics, and the fundamental laws of physics can be unified into a single theory. As our understanding of black holes grows, we move ever closer to this goal. But this journey is not just about finding answers, it is also about asking better questions. Every new discovery about black holes leads to new mysteries, new areas for exploration, and new ways of thinking about the universe. For example, the detection of gravitational waves from black hole mergers has opened a new era of astronomy. These ripples in space-time, first observed by LIGO in 2015, provide a completely different way of observing the universe. By studying gravitational waves, scientists are able to probe the properties of black holes in ways that were previously impossible. They are able to measure their masses, spins, and even their collisions, shedding light on the dynamic behavior of these enigmatic objects. In this sense, black holes are not just passive objects. They are active agents in the universe, shaping the fabric of space-time and producing observable effects that ripple across the cosmos. These discoveries are just the beginning. As our observational tools improve, and as new theories of quantum gravity are developed, we will continue to learn more about the behavior of black holes and their role in the universe. Perhaps one day, we will be able to peer into the very heart of a black hole, to understand what lies within the event horizon and uncover the true nature of the singularity. Until then, black holes remain some of the most profound and mysterious objects in the universe. Their formation, their behavior, and their ultimate fate all point to deep questions about the nature of reality itself. They are reminders that, even in a universe that we are beginning to understand, there are still vast unknowns waiting to be explored. The cosmic journey that leads from the formation of a black hole to its long-term evolution remains a mystery full of surprises and subtleties. After the initial collapse, once the singularity and event horizon have been formed, the black hole begins its life as a quiet, enigmatic object, seemingly devoid of change. However, this is far from the case. Despite its simplicity, the black hole's interaction with its environment is anything but passive. The way a black hole grows, the way it disturbs its surroundings, and the way it leaves its mark on the fabric of space-time reveal much about the underlying forces shaping the universe. A black hole can continue to grow in mass over time, not by fusion, as stars do, but by accreting material from its environment. This material may come from a companion star in a binary system, from the surrounding interstellar gas, or even from other black holes in a merger event. As matter falls toward the black hole, it forms an accretion disk, an extremely hot and dense region of matter that spirals inward under the influence of gravity. As it moves closer to the event horizon, the material in the accretion disk experiences immense friction and compression, heating up to temperatures of millions of degrees. This extreme heat causes the material to emit high-energy radiation, which can be observed in various wavelengths, from X-rays to radio waves. The energy released by this accretion process is a key signature of a black hole's presence. Without this external material, a black hole would remain largely invisible, its mass and gravity detectable only through their effect on nearby objects. But when it actively pulls in matter, the black hole becomes a radiant source of energy. These accreting black holes can often outshine entire galaxies, forming what we call quasars. A quasar is an extremely luminous and active galactic nucleus, powered by the accretion of material into a supermassive black hole. These objects are often found in the centers of distant galaxies and can emit more energy than all the stars in the galaxy combined. Quasars are one of the most powerful sources of light and radiation in the universe, and they provide us with valuable insight into the behavior of black holes, the evolution of galaxies, and the large-scale structure of the cosmos. In addition to the energy produced by the accretion disk, black holes can also launch powerful jets of high-energy particles. These jets, which are often observed as narrow beams of radiation extending from the poles of the black hole, are a direct consequence of the extreme conditions near the event horizon. The exact mechanism that powers these jets is still not fully understood, but it is believed that the black hole's magnetic field, combined with its rapid rotation, plays a crucial role. The magnetic field channels energy and matter along the black hole's axis of rotation, accelerating particles to nearly the speed of light and sending them outward in narrow beams. These jets can extend for thousands of light years, and their interaction with the surrounding gas can have a profound effect on the surrounding environment. They can heat up intergalactic gas, trigger star formation, or even inhibit it by clearing out gas that would otherwise collapse into new stars. Jets are another way in which black holes actively shape their surroundings, making them more than just isolated points in space. They are key players in the larger dynamics of galaxies, regulating the growth and evolution of galaxies and clusters of galaxies. However, black holes are not only defined by their accretion processes and their ability to interact with nearby matter. Even without accreting material, black holes continue to affect the universe in profound ways. The most subtle and yet perhaps the most profound influence of a black hole is its ability to bend space-time itself. As predicted by Albert Einstein's theory of general relativity, the gravitational field of a black hole curves the fabric of space-time, creating a region where the normal rules of motion break down. Time slows down near the event horizon, and the paths of objects are distorted in ways that are unimaginable in the normal universe. This warping of space-time is not just a theoretical concept. It has been confirmed by numerous observations. For instance, the orbits of stars near the supermassive black hole at the center of the Milky Way provide evidence for the bending of space-time. By observing how stars move in the vicinity of this black hole, scientists can measure the curvature of space-time and infer the mass and other properties of the black hole itself. This bending of space-time also provides the basis for the detection of gravitational waves. These ripples in space-time were first predicted by Einstein in 1915, but only recently have we been able to detect them directly. Gravitational waves are produced by accelerating masses, such as two black holes merging. When black holes merge, they release a burst of gravitational waves that ripple outward, traveling across the universe at the speed of light. These waves carry information about the masses, spins, and other properties of the black holes involved in the merger. The detection of gravitational waves is a groundbreaking achievement in astrophysics, providing a new way to study black holes and other extreme objects in the universe. It is a testament to the power of black holes to disturb space-time itself, even at vast distances. Yet even as we detect these ripples in space-time, we must acknowledge the many mysteries that remain. The most profound of these is the question of what happens to matter and information once it crosses the event horizon. While we have learned much about black holes by observing their effects on the surrounding environment, we are still in the dark about what happens within. This singularity, at the heart of every black hole, is a place where our current understanding of physics breaks down. It is a region where quantum mechanics and general relativity, two pillars of modern physics, must be reconciled. Some theorists believe that the singularity is not a point at all, but a region where space-time itself becomes infinitely curved. Others propose that quantum effects could prevent the formation of a true singularity, offering a resolution to the paradoxes that arise from the collapse of matter into a black hole. Until we have a complete theory of quantum gravity, however, the ultimate nature of the singularity remains a mystery. Still, the search for answers continues. As new telescopes and detectors come online, and as our theoretical models improve, we move ever closer to understanding the final frontier of black holes. What happens when we reach the event horizon? How does the information that falls into a black hole behave? Can we ever probe the interior of a black hole, or is it forever hidden from view? These questions remain at the forefront of modern astrophysics, and their answers will likely shape our understanding of space, time, and the very nature of the universe itself. Until then, black holes will continue to captivate our imaginations and challenge our understanding of the cosmos, standing as some of the most complex, mysterious, and fascinating objects in the universe. From the birth of a black hole through stellar collapse to the ongoing study of their effects on their surroundings, black holes are not just objects of study. They are windows into the most profound mysteries of the universe. They are reminders of the limits of our knowledge and of the vastness of what remains to be discovered. Despite the many questions that remain unanswered about black holes, their study has provided valuable insights into the nature of space, time, and gravity. One of the most important lessons from black hole research is that the universe operates according to principles that challenge our intuitions and force us to rethink our understanding of the fundamental laws of nature. Black holes are the ultimate expression of how gravity shapes the cosmos, but they also reveal how other forces such as electromagnetism, nuclear forces, and quantum mechanics interact in extreme conditions. As we explore the formation, growth, and evolution of black holes, we gain a deeper understanding of the processes that govern the behavior of matter and energy in the universe. However, the complexity of black holes forces us to confront the limits of our current theories. For example, the fact that general relativity and quantum mechanics both break down at the singularity suggests that these two theories, which have proven so successful in their respective domains, may not be complete. A unified theory of quantum gravity, which combines the principles of both general relativity and quantum mechanics, remains one of the holy grails of modern physics. Black holes thus present a fundamental challenge to our understanding of the universe, one that requires a new framework of thought. In addition to their theoretical significance, black holes also play an important role in shaping the universe on large scales. They are not just the endpoints of massive stars, but are integral to the structure and dynamics of galaxies. The supermassive black holes that reside at the centers of galaxies act as central engines, influencing the formation and evolution of stars, gas, and dust around them. These black holes are thought to regulate the growth of their host galaxies through feedback mechanisms. The energy they release during accretion in the form of radiation and powerful jets can heat surrounding gas and prevent it from cooling and condensing into new stars. This feedback process helps to explain why some galaxies, particularly massive ones, have relatively low rates of star formation despite having large amounts of available gas. Without black holes, galaxies would likely look very different, perhaps more active, but also potentially less stable. The feedback from black holes may even be responsible for the observed relationship between the mass of the central black hole and the properties of the galaxy it inhabits. This relationship, known as the M-sigma relation, suggests that the mass of a galaxy's central black hole is tightly linked to the velocity dispersion of stars in its bulge. The origin of this correlation is still a subject of active research, but it hints at a deep connection between the formation and growth of black holes and the development of galaxies as a whole. The formation of supermassive black holes is another unresolved puzzle in astrophysics. While we have a good understanding of how stellar mass black holes form through the collapse of massive stars, the process by which supermassive black holes come into existence is more complex. Current models suggest that they may form through the direct collapse of massive clouds of gas in the early universe, bypassing the usual stellar evolution process. Alternatively, they could grow gradually by accreting gas and merging with other black holes over time. Observations of the most distant quasars indicate that supermassive black holes must have formed within the first few 100 million years after the Big Bang. This suggests that these black holes grew quickly, perhaps through a combination of rapid accretion and mergers. The formation of these early supermassive black holes may have played a key role in the reionization of the universe, when the first stars and galaxies formed and began to ionize the surrounding hydrogen gas. The interplay between black holes, galaxies, and the intergalactic medium is a central aspect of the ongoing study of cosmic evolution. In addition to their importance in galaxy formation, black holes also provide valuable insights into the nature of space-time itself. One of the most profound predictions of general relativity is the existence of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. black holes are among the most efficient producers of gravitational waves, particularly when they merge. The detection of gravitational waves from black hole mergers has opened a new window into the universe, allowing us to observe objects that would otherwise be invisible. These detections provide a wealth of information about the masses, spins, and orbits of black holes, and they've already yielded several unexpected results. For example, the first detection of gravitational waves made by LIGO in 2015 revealed the merger of two black holes with masses that were much larger than expected. These observations challenge our models of black hole formation and suggest that the population of black holes in the universe may be more diverse than previously thought. The detection of gravitational waves also raises the possibility of observing other types of exotic phenomena, such as neutron star mergers or the collision of black holes with other compact objects. In the future, more sensitive detectors may allow us to observe the early stages of black hole formation, providing a direct glimpse into the collapse of massive stars. The study of black holes is thus closely tied to the development of new observational techniques, and it is through these techniques that we are learning more about the most extreme objects in the universe. In addition to gravitational waves, black holes also produce other types of radiation that are detectable with modern telescopes. For example, the accretion disks around black holes emit X-rays, which can be observed using space-based observatories. These X-ray observations provide detailed information about the behavior of matter near the event horizon, including the structure of the accretion disk, the presence of relativistic jets, and the dynamics of the material falling into the black hole. By studying the spectra of X-rays emitted by these disks, astronomers can infer the spin, mass, and other properties of the black hole. However, despite all of the advances in black hole research, many mysteries remain. What happens inside the event horizon? How does the matter and energy behave near the singularity? Can we ever detect the signature of quantum effects in the strong gravitational fields near a black hole? Will the search for a theory of quantum gravity provide the answers we seek? These questions are at the heart of the ongoing study of black holes, and they drive much of the current research in theoretical physics and astrophysics. In many ways, black holes serve as the ultimate testbed for our understanding of the universe. Their extreme conditions push the limits of our knowledge, challenging us to reconcile our best theories of gravity and quantum mechanics. Yet they also provide a glimpse into the most fundamental aspects of nature. As we continue to probe the mysteries of black holes, we not only learn more about these fascinating objects, but also about the very structure of space and time itself. In the end, black holes are more than just cosmic oddities. They are profound objects that connect the micro and macroscopic scales of the universe, offering insights into both the smallest particles and the largest cosmic structures. The journey of discovery that they inspire will shape our understanding of the cosmos for generations to come. As our understanding of black holes deepens, we begin to appreciate not only their influence on the universe, but also their connection to the most fundamental questions of existence. One of the most intriguing aspects of black holes is their role as bridges to understanding the limits of physics itself. Black holes bring together the two most successful theories of the modern era, general relativity and quantum mechanics. These theories, despite their remarkable successes, are fundamentally incompatible when applied to the extreme environments near a black hole's singularity. General relativity describes the behavior of large-scale objects like planets, stars, and galaxies, and it predicts the formation of black holes as a result of gravitational collapse. Meanwhile, quantum mechanics governs the behavior of subatomic particles, with its principles leading to phenomena like wave-particle duality and the uncertainty principle. The gap between these two theories has long been a subject of intense debate and research, with black holes serving as a focal point for scientists attempting to unify them. The singularity, the point of infinite density at the center of a black hole, is the region where general relativity and quantum mechanics both break down. In this realm, the curvature of spacetime is so extreme that quantum effects are expected to dominate. However, our current theories of gravity and quantum mechanics provide conflicting predictions about the behavior of matter and energy at these scales. Resolving this conflict is one of the major challenges of modern physics. A unified theory of quantum gravity would reconcile these two frameworks, providing a comprehensive understanding of the universe at all scales, from the infinitesimally small to the infinitely large. This theory could potentially reveal new insights into the nature of space, time, and the fundamental forces of nature. It might explain how space-time itself behaves at the Planck scale, the smallest scale of the universe, and how quantum particles interact with gravity in the extreme environments near a black hole. Until a theory of quantum gravity is developed, black holes remain one of the most important and enigmatic objects in the universe, offering glimpses into the unknown and pushing the boundaries of our understanding of the laws of nature. Another key area of black hole research involves the study of Hawking radiation. Proposed by physicist Stephen Hawking in 1974, Hawking radiation is a theoretical prediction that black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This radiation arises from the creation of particle-antiparticle pairs in the vacuum of space. Normally, these pairs would annihilate each other and disappear, but near the event horizon, one particle may fall into the black hole while the other escapes, resulting in the emission of radiation. Over time, this process causes the black hole to lose mass and energy, eventually leading to its evaporation. The idea that black holes can lose mass and energy through Hawking radiation challenges the long-held belief that nothing can escape a black hole. It also has profound implications for the fate of black holes and the nature of information in the universe. If a black hole evaporates through Hawking radiation, it would eventually disappear, leaving no trace of the information that it contained. This creates a paradox known as the black hole information paradox, which has yet to be resolved. According to quantum mechanics, information cannot be lost, but if a black hole evaporates completely, it would seem to violate this principle. One possible resolution to this paradox is that the information is not truly lost, but is instead encoded in the radiation emitted by the black hole. Another possibility is that the information is somehow preserved on the event horizon itself, in a phenomenon known as the holographic principle. This principle suggests that all the information about a black hole's interior may be encoded on its surface, much like a hologram encodes a three-dimensional image on a two-dimensional surface. The search for a solution to the black hole information paradox is one of the most exciting and active areas of research in theoretical physics. It could potentially provide deep insights into the nature of quantum mechanics, the nature of gravity, and the structure of space-time. It may also have implications for our understanding of the fundamental nature of reality itself. The exploration of black holes also raises profound philosophical questions about the nature of space, time, and the universe. The concept of the event horizon, the boundary beyond which nothing can escape, challenges our understanding of causality and the flow of time. From the perspective of an observer far away from the black hole, time appears to slow down as an object approaches the event horizon, with the object seemingly frozen in time at the edge. However, from the perspective of the object itself, time continues normally, and it crosses the event horizon without any noticeable delay. This apparent contradiction between the different perspectives highlights the complexity of space-time near a black hole and invites further contemplation of the nature of time itself. Additionally, the idea of the singularity, where space-time becomes infinitely curved and the known laws of physics break down, raises profound questions about the limits of human knowledge. It suggests that there are aspects of the universe that may be fundamentally unknowable, and that our current theories may not be sufficient to fully describe the cosmos. This realization, while humbling, also drives scientific inquiry, as it pushes us to explore new ideas and new frameworks for understanding the universe. Black holes also serve as natural laboratories for studying the most extreme physical conditions. The environment near a black hole is unlike anything we can reproduce on Earth, with temperatures, pressures, and densities far beyond the capabilities of current experimental facilities. By studying the behavior of matter and energy in these extreme conditions, scientists can test the limits of our physical theories and gain new insights into the fundamental forces of nature. For example, the study of accretion disks and relativistic jets provides valuable information about the behavior of matter under extreme gravitational and electromagnetic forces. The study of gravitational waves from black hole mergers allows us to probe the nature of space-time itself, and the detection of Hawking radiation could offer clues about the behavior of quantum gravity. In many ways, black holes are the ultimate test of our understanding of the universe. They challenge our theories, push the boundaries of our knowledge, and inspire us to seek deeper truths about the nature of reality. The study of black holes is not just a scientific endeavor, it is a journey into the unknown, a quest to understand the most fundamental aspects of space, time, and the laws of physics. As we continue to explore these mysterious objects, we're not only unraveling the secrets of black holes themselves, but also gaining a deeper understanding of the universe as a whole. The future of black hole research holds immense promise. With new telescopes, more powerful computers, and groundbreaking observational techniques, we will continue to probe the depths of these enigmatic objects. We may one day unlock the mysteries of the singularity, understand the nature of quantum gravity, and solve the black hole information paradox. Until then, black holes remain as fascinating and mysterious as ever, their presence a reminder of the complexity and beauty of the cosmos. The study of black holes not only challenges the boundaries of current physics, but also provides essential insights into the larger processes governing the universe. Black holes, despite their eerie and seemingly simple nature, play a pivotal role in shaping the cosmos. Their formation, growth, and eventual interactions with other objects leave behind a series of observable signatures that allow astronomers to track their behavior across cosmic distances. But perhaps most intriguingly, black holes also reveal the deepest mysteries of space-time. The warping of space-time around a black hole is not merely a theoretical construct, but something that can be observed and measured. As light passes near a black hole, it bends, a phenomenon known as gravitational lensing. This effect allows astronomers to observe distant galaxies and stars that would otherwise be obscured by the black hole's gravitational pull. In essence, black holes act as cosmic magnifying glasses, revealing the hidden structure of the universe. The way light and other forms of radiation interact with the intense gravitational field near a black hole provides valuable clues about the nature of space and time. For example, the way light is redshifted as it escapes from near a black hole offers insights into the warping of space-time. The stronger the gravitational field, the more the light is stretched, shifting it toward longer wavelengths, or redder, as it climbs out of the gravitational well. This effect is most pronounced near the event horizon, the point beyond which light cannot escape. Studying these redshifted emissions allows scientists to infer the structure and behavior of the accretion disk and the properties of the black hole itself. As black holes continue to captivate our imagination, they also serve as testbeds for new theories about the fundamental nature of the universe. The extreme conditions near a black hole offer the possibility of studying matter, energy, and gravity in ways that were previously unimaginable. For example, the combination of strong gravity and quantum effects near the event horizon provides an opportunity to explore the interface between general relativity and quantum mechanics. These two theories, which have been extraordinarily successful in their respective domains, do not yet have a common framework. The search for quantum gravity, the theory that would merge the two, is one of the most exciting frontiers of modern physics. Black holes, with their extreme environments, are a natural laboratory for studying quantum gravity. The behavior of matter near the event horizon, particularly in the context of Hawking radiation, may provide valuable insights into the nature of space-time at the smallest scales. It is possible that black holes could hold the key to understanding the most profound questions about the universe, including the true nature of space-time and the origin of the cosmos itself. One of the most fascinating aspects of black hole research is the role they play in the evolution of galaxies. Observations of supermassive black holes at the centers of galaxies suggest that these objects are intimately connected to the growth and evolution of their host galaxies. The mass of a galaxy's central black hole is closely related to the properties of the galaxy itself, including the size of its bulge, the distribution of stars, and the velocity dispersion of its stars. This connection between black holes and galaxies suggests that the growth of black holes may influence the formation of galaxies, and vice versa. The process of accretion, where material falls toward the black hole and emits radiation, has profound effects on the surrounding gas. In some cases, the energy released by the accretion disk can heat the surrounding gas to such high temperatures that it prevents it from cooling and collapsing into new stars. This feedback mechanism can regulate the rate of star formation within the galaxy, influencing its overall evolution. In addition to influencing star formation, black holes can also shape the large-scale structure of the universe through their role in galaxy mergers. As galaxies collide and merge, their central black holes can eventually coalesce into a single, more massive black hole. This process, known as a black hole merger, generates an immense amount of energy in the form of gravitational waves. These waves travel across the universe, carrying information about the black holes involved in the merger. The detection of these waves, first achieved in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, has opened a new window into the study of black holes and their interactions. Gravitational waves provide a direct way to measure the masses, spins, and other properties of black holes, offering a unique perspective on their behavior. The merger of two black holes is not just a dramatic event, it is also a key moment in the evolution of galaxies. As black holes merge, they release large amounts of energy that can alter the dynamics of the surrounding gas and stars. This process has the potential to influence the growth and evolution of galaxies over cosmic timescales. It may also play a role in the formation of supermassive black holes in the early universe, when galaxies were still forming and growing. As we continue to detect and study gravitational waves, we will gain a deeper understanding of the role that black holes play in shaping the universe. These observations will also help to refine our models of black hole formation and evolution, shedding light on the many processes that govern the lives of these enigmatic objects. In addition to their role in galaxy formation and evolution, black holes also raise important philosophical questions about the nature of the universe itself. The event horizon, which marks the boundary between the observable universe and the hidden interior of the black hole, raises questions about causality and the flow of time. As light and matter approach the event horizon, time appears to slow down from the perspective of a distant observer. This phenomenon, known as time dilation, suggests that time itself is not a fixed and absolute quantity, but is instead affected by the gravitational field of a black hole. This raises profound questions about the nature of time and its relationship to space. The fact that the event horizon acts as a boundary that separates the observable from the unobservable also raises questions about the nature of information. When an object falls into a black hole, its information seems to be lost forever. This idea has led to the development of the black hole information paradox, which challenges the foundations of quantum mechanics. According to the principles of quantum theory, information can never be truly lost. Yet, when matter falls into a black hole, it appears to disappear, leaving behind only the mass, charge, and spin of the black hole. The resolution of this paradox is still an open question in physics, but it underscores the deep connection between black holes and our understanding of the fundamental laws of nature. Ultimately, the study of black holes is not just about understanding these enigmatic objects themselves, but about exploring the most profound questions in physics and cosmology. By studying black holes, we're not only learning about the extreme environments they create, but also about the nature of space, time, and the universe as a whole. Black holes, with their paradoxes and mysteries, challenge our most basic assumptions and push the limits of human knowledge. As we continue to probe their depths, we will undoubtedly uncover new insights into the fabric of the cosmos, revealing truths that are yet beyond our imagination. In this sense, black holes are not just a scientific curiosity. They're a symbol of the infinite possibilities that remain in the vast and mysterious universe. As we continue to explore the mysteries of black holes, one thing becomes clear. Their existence is intrinsically tied to the evolution of the universe itself. From the formation of the first black holes in the early universe to the growth of supermassive black holes at the centers of galaxies, black holes have played a key role in shaping the cosmic landscape. The interplay between these objects and the galaxies, stars, and gas that surround them has driven the evolution of the universe on both large and small scales. Understanding black holes not only helps us learn more about these enigmatic objects, but also provides insight into the fundamental nature of the cosmos. One of the most intriguing aspects of black hole research is how it challenges our understanding of the very fabric of space and time. In the region near a black hole's event horizon, the curvature of space-time becomes so extreme that the normal rules of physics no longer apply. In this extreme environment, gravity is so strong that it warps the path of light, bends time, and distorts space itself. This distortion of space-time has profound implications for our understanding of the universe. For example, the warping of space-time near a black hole suggests that gravity is not just a force that acts on matter, but is a manifestation of the way space-time itself behaves. This realization has led to a deeper understanding of the nature of gravity and its connection to the structure of the universe. The study of black holes also reveals the dynamic nature of space-time. The fact that black holes can distort time and space challenges the traditional view of the universe as a static backdrop for the motion of objects. Instead, it suggests that the universe is a dynamic, ever-changing entity, where gravity and other forces constantly shape the structure of space and time. As black holes continue to grow and merge, they send ripples through space-time in the form of gravitational waves, which travel across the universe and carry information about the black holes involved in the collision. The detection of these gravitational waves has opened up a new window into the study of black holes, allowing scientists to probe their properties and study the dynamics of black hole mergers. This new method of observation has the potential to provide a wealth of information about the behavior of black holes and the nature of space-time itself. While much of the study of black holes focuses on their interactions with their surroundings, it is also important to recognize the role that black holes play in the larger cosmic picture. As mentioned earlier, black holes are believed to reside at the centers of most galaxies, including our own Milky Way. These supermassive black holes, which can have masses millions or even billions of times that of the Sun, are thought to influence the formation and evolution of galaxies. The gravitational pull of these black holes can shape the orbits of stars and gas in the galaxy, dictating the dynamics of the entire system. This interaction between black holes and galaxies is believed to be a crucial factor in the formation of large-scale structures in the universe. The connection between black holes and galaxy formation also extends to the large-scale evolution of the universe. Supermassive black holes are thought to play a role in the reionization of the universe, a process that occurred roughly 500 million years after the Big Bang. During reionization, the first stars and galaxies began to form, and their radiation ionized the hydrogen gas that filled the universe. This process marked the end of the cosmic dark ages and set the stage for the formation of the first galaxies, stars, and black holes. The energy released by the accretion of matter onto supermassive black holes may have contributed to this process, helping to heat the surrounding gas and trigger the reionization of the universe. The study of black holes also provides a window into the distant past of the universe. By observing the light emitted by quasars, which are powered by supermassive black holes, astronomers can study the earliest galaxies and black holes in the universe. These observations allow scientists to probe the conditions of the universe during its infancy, providing valuable insights into the formation of galaxies and black holes. The study of black holes is also intimately connected to the study of dark matter and dark energy, two of the most mysterious and elusive substances in the universe. While dark matter and dark energy cannot be directly observed, their presence can be inferred by studying the behavior of galaxies and other cosmic structures. Some researchers have proposed that black holes may be connected to dark matter, either through the formation of primordial black holes in the early universe or through their role in the gravitational interactions of dark matter particles. Others have suggested that black holes may be a key component of the large-scale structure of the universe, influencing the distribution of galaxies and other cosmic objects. While much remains to be learned about the relationship between black holes, dark matter, and dark energy, it is clear that the study of black holes offers important clues about the nature of the universe as a whole. Another fascinating aspect of black holes is their potential to challenge our understanding of the concept of time. Time behaves very differently near a black hole than it does in the everyday world. As an object approaches the event horizon, time appears to slow down relative to an observer far away. To an outside observer, it would seem as though the object is frozen in time as it approaches the event horizon, unable to cross it. However, from the perspective of the object itself, time continues to pass normally, and it crosses the event horizon without any noticeable delay. This strange behavior of time near a black hole raises important questions about the nature of time itself. Is time an absolute quantity, or is it relative to the observer? How does gravity affect the flow of time? And what does this tell us about the relationship between space, time, and gravity? These are questions that remain unanswered, but they highlight the deep connection between black holes and the fundamental nature of the universe. The study of black holes, in essence, is a study of the most extreme conditions in the universe, a journey into the depths of space-time and the boundaries of human understanding. As we continue to explore these objects, we not only learn more about black holes themselves, but also about the fundamental nature of space, time, and gravity. Black holes offer a unique opportunity to test the limits of our theories and explore the most profound questions about the structure of the universe. In doing so, they challenge us to rethink our understanding of the laws of nature and inspire us to seek answers to the deepest mysteries of existence. As we continue to investigate the role of black holes in the universe, we will undoubtedly encounter new surprises and discoveries. With new observational techniques, improved computational models, and advances in theoretical physics, we're just beginning to scratch the surface of the many secrets that black holes hold. In the end, black holes represent not only the most extreme and mysterious objects in the cosmos, but also the greatest opportunities for advancing our understanding of the universe itself. They are the key to unraveling the deepest mysteries of space, time, and the nature of reality. The continued exploration of black holes brings us to the frontier of both observational astronomy and theoretical physics. As we push further into the unknown, new discoveries and observations deepen our understanding of how these enigmatic objects affect their surroundings. One of the most intriguing aspects of black holes is their role in shaping the cosmic structures around them, particularly galaxies and galaxy clusters. The gravitational influence of a supermassive black hole at the center of a galaxy is far-reaching. These black holes affect the motion of stars, gas, and even dark matter within their galaxies, playing a critical role in the dynamics of these systems. The larger the black hole, the greater its influence. Supermassive black holes, with masses ranging from millions to billions of solar masses, are thought to be present at the center of almost every large galaxy in the universe. These black holes are not passive. Rather, they are active engines that drive many of the most energetic processes in the cosmos. The most significant of these processes is accretion. When a black hole pulls material from its surroundings, the resulting accretion disk releases immense amounts of energy as the material is heated to incredibly high temperatures. This radiation can illuminate vast regions of space, allowing us to detect black holes billions of light years away. In fact, some of the most distant objects we observe, quasars, are powered by supermassive black holes. A quasar is a highly energetic and luminous object that emits more energy than an entire galaxy of stars. Quasars can outshine the combined light of the galaxy that hosts them, making them visible across vast distances. The energy produced by a quasar is the result of material being accreted into a black hole. As the material spirals inward, it forms an accretion disk that radiates across the electromagnetic spectrum, from radio waves to X-rays. Quasars are crucial for understanding the evolution of galaxies and the growth of supermassive black holes. They represent the active phase in the life of a black hole, where it is consuming vast amounts of material and emitting intense radiation. The study of quasars allows astronomers to probe the early universe, as many quasars are found at great distances, corresponding to a time when the universe was much younger. Quasars also offer important clues about the relationship between black holes and galaxy formation. It is thought that the growth of a supermassive black hole is closely tied to the development of its host galaxy. The presence of a black hole can regulate the formation of new stars in the galaxy through a process known as feedback. The energy released by the accretion disk or relativistic jets can heat surrounding gas, preventing it from cooling and collapsing into new stars. This feedback mechanism is believed to play a key role in the evolution of galaxies, especially the most massive ones. The formation of supermassive black holes in the early universe is another puzzle that remains unsolved. Observations of distant quasars indicate that supermassive black holes were already in place less than 1 billion years after the Big Bang. This raises the question, how did these black holes form so quickly? There are two main theories that attempt to explain the rapid formation of supermassive black holes. One suggests that these black holes form through the direct collapse of massive clouds of gas in the early universe, bypassing the usual process of stellar evolution. The other theory proposes that these black holes grew gradually by accreting gas over time. While both models are plausible, it is still unclear which one is correct. The study of the first supermassive black holes in the universe is an area of active research, with astronomers using advanced telescopes to look for clues in the light emitted by distant quasars. Understanding the formation of these black holes could provide insights into the conditions of the early universe and the processes that led to the formation of the first galaxies. Another important aspect of black hole research is the detection and study of gravitational waves. These ripples in space-time, first predicted by Albert Einstein in 1915, were directly observed for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are produced by the acceleration of massive objects, such as the collision and merger of black holes. When two black holes spiral toward each other and merge, they release a burst of gravitational waves that travel across the universe. By studying these waves, astronomers can learn about the properties of the black holes involved in the merger, including their masses, spins, and the dynamics of the collision. The detection of gravitational waves has opened a new window into the study of black holes, allowing scientists to directly observe these events without relying on electromagnetic radiation. Gravitational wave astronomy is still in its infancy, but it holds great promise for advancing our understanding of black holes and their role in the universe. In particular, the detection of gravitational waves from black hole mergers provides a new way to probe the population of black holes in the universe, including those that are otherwise difficult to observe. These mergers are also crucial for understanding the growth of supermassive black holes. As black holes merge and grow over time, they release gravitational waves that can be detected by instruments like LIGO. By studying the frequency and characteristics of these waves, scientists can gain insight into the evolution of black hole populations and the role they play in the large-scale structure of the universe. Yet, despite these advancements, black holes continue to challenge our understanding in ways that go beyond the realm of observation. The most fundamental of these challenges is the nature of the singularity, the point at the heart of a black hole where gravity becomes infinite and space-time curvature becomes extreme. According to general relativity, the singularity is a region where the laws of physics break down. The infinite density and curvature of space-time at this point are beyond the reach of our current theories. To fully understand black holes, we need a theory that can describe the behavior of matter and energy at the singularity, and one that can reconcile the principles of quantum mechanics with general relativity. This theory, known as quantum gravity, is still a work in progress. Several approaches, including string theory and loop quantum gravity, aim to provide a unified description of gravity and quantum mechanics. However, a complete theory of quantum gravity has yet to be developed. The singularity remains one of the most profound mysteries in modern physics. It challenges our understanding of space, time, and the fundamental nature of reality. Despite the many unknowns, the study of black holes continues to push the boundaries of scientific inquiry. As new observational techniques, such as gravitational wave astronomy, provide fresh insights into black hole behavior, and as new theoretical models of quantum gravity emerge, we move closer to unraveling the most profound mysteries of the universe. Black holes are not only fascinating objects in their own right, but they are also key to understanding the broader nature of the cosmos. They provide a unique opportunity to explore the intersection of gravity, quantum mechanics, and the fundamental laws of physics, offering profound insights into the nature of space, time, and the universe itself. As the story of black holes draws us deeper into the mysteries of the universe, it ultimately brings us to the boundaries of what we can observe, model, and understand. In every way, black holes are thresholds, physical, mathematical, and philosophical. They are regions of space where gravity overpowers all other forces, where light itself cannot escape, and where the known laws of physics begin to unravel. And yet, for all their extreme qualities, black holes are not rare or anomalous. They are natural endpoints for the most massive stars and essential components in the formation and evolution of galaxies. They're not just exotic features of the cosmos, but central players in its ongoing transformation. One of the most profound implications of black holes lies in their apparent permanence. Once a black hole is formed, it is extraordinarily difficult to destroy. Unlike stars that shine, burn out, and scatter their elements back into space, a black hole consumes matter and energy, locking them away behind the event horizon. This one-way barrier gives black holes a reputation for finality. However, the prediction of Hawking radiation complicates this picture. If black holes can emit radiation and slowly lose mass, then they are not eternal after all. Over vast spans of time, trillions upon trillions of years, a black hole may gradually shrink, evaporate, and vanish. Yet the evaporation process is so slow for large black holes that no such event has ever been observed. For now, all the black holes we know of seem stable, ancient, and enduring. Their slow evaporation is a reminder that even the most powerful structures in the universe are subject to change and decay, given enough time. This slow decay also revives the question of information. If black holes eventually vanish, what happens to the information about the matter they have consumed? Is it encoded in the Hawking radiation, subtly imprinted in the quantum fluctuations at the horizon? Or is it truly lost, violating one of the most sacred principles of quantum mechanics? This unresolved paradox, whether information is preserved or destroyed in black holes, has divided physicists for decades and remains one of the great open questions in theoretical physics. The holographic principle, developed in part from the study of black holes, suggests that all the information contained in a volume of space can be described by data encoded on its boundary. If true, it would mean that everything falling into a black hole is somehow recorded on the event horizon. This idea, while still under investigation, offers a tantalizing possibility. That the event horizon itself may not just be a passive boundary, but a dynamic surface where the information content of the black hole is preserved. The consequences of such a principle extend far beyond black holes. They hint at a radically different understanding of reality, one in which space, time, and information are woven together in unexpected ways. They suggest that the universe might operate more like a quantum computation than a classical machine, and that what we perceive as continuous space might emerge from a deeper, discrete structure. These are not idle speculations. They are the direct results of trying to resolve the contradictions that arise when black holes are taken seriously as physical objects rather than mathematical abstractions. As we move into the era of precision cosmology and gravitational wave astronomy, black holes are becoming less abstract and more tangible. The ripples in space-time detected by observatories like LIGO and Virgo provide real-time evidence of black hole interactions. Each detection is not only a confirmation of theory, but a data point in the growing population of known black holes. We now know that black holes come in a wider variety of masses and combinations than previously expected. Some are remnants of stars only a few times more massive than the Sun, while others formed in the dense early universe and grew to immense size. Their mergers provide clues about the environments they inhabit: dense stellar clusters, galactic cores, or remnants of ancient galaxies. The pattern of these signals, how often black holes merge, what their masses are, how fast they spin, tells a story about how stars live and die, how galaxies form and collide, and how structure builds up over cosmic time. Still, black holes challenge us to see the universe differently. They remind us that the visible world is only a small part of what exists. Most of a black hole's activity is hidden, behind the event horizon, beyond the reach of light, but through gravitational waves, bending light, and the motion of surrounding stars and gas, we can trace their influence. This indirect observation is a skill astronomy has always honed, measuring the unseen by its effects, learning about the distant by the light that reaches us. Black holes are the culmination of this approach, invisible, untouchable, and yet profoundly influential. They also echo with a kind of cosmic poetry. A black hole begins as a star, bright, warm, generative. Through collapse, it becomes an object of silence and density, no longer emitting light but shaping everything around it. In this transformation, there is a shift from illumination to gravity, from fusion to curvature, yet nothing is wasted. The matter that formed the star still exists, reshaped into a new form. The black hole that results still tells the story of the star that came before. It is encoded in the mass, the spin, and the curvature of space itself. Even if no light escapes, the gravitational influence never stops. The black hole becomes an invisible sculptor, guiding the orbits of stars, shaping the flow of gas, marking the places where galaxies grow, and eventually where they end. In the far future of the universe, when the last stars have gone dark and galaxies have drifted apart, black holes may be the final structures to endure. They will outlive the light, outlive the stars, perhaps even outlive the matter we now understand. Their slow evaporation through Hawking radiation, stretching across unimaginable timescales, may be the final act of cosmic evolution. When the last black hole fades into quantum whispers, the universe will enter a state of deep, quiet stillness, emptied of light, structure, and form. And yet through it all, black holes offer something else, a guide to the limits of what we know and what we can know. They are thresholds in more than one sense, doors to regions of space-time we cannot explore, puzzles that force our theories to evolve, and mirrors reflecting the unfinished work of science. In their silence, there is clarity. In their darkness, insight. In their collapse, a call to explore deeper, ask better, and imagine further. As we observe the cosmos from nearby stars to distant galaxies, from the flicker of X-rays to the tremble of gravitational waves, black holes remain a reminder that the universe is not only vast, but mysterious, structured by laws we are still learning to read. Their formation, from collapsing stars, is one chapter in a long story, one still unfolding, one we are privileged to witness, and, slowly, to understand.